Alright, so welcome to part 2 of this demo where I'm trying to explain how to do a nearest neighbors algorithm in C++ inside an R package. And so I think I figured out what was going on last time. And so when we defined our C method definition here, we always have to terminate this with with a null entry. And so I think that's the reason why it was not built before. Let's try that. So indeed, it's that was the issue. And so now what we can do is we can see that we can probably use this .c function. Right, so our .c worked and it gives us some result, but what it gives us is this kind of a trivial result that doesn't really tell us much because we haven't really coded the nearest neighbors algorithm yet. So let's do that. So first thing that we should do when we're looking at coding the nearest neighbors algorithm, well, we're going to have to compute the distances between all of the test point and all of the training points. And to make that super easy, we're going to be using the Eigen library to wrap the pointers and give us some nice matrix vector operations. So to get access to the Eigen library, we use pound include Eigen/dense. So that refers to dense matrices as opposed to sparse matrices. If we recompile now, we're going to get this compilation error, eigendense, no such file or directory. To fix that, we can go back to the description file and we can add a line linking to RcppEigen. And so that's a package that has these eigen header files. So if we recompile now, it's going to tell R to point to those header files in that package, and then it compiles just fine. You can see this -i line, which we just added to the library RcppEigen, which now is being used to avoid that compilation error. And so now what we can do is we can start writing our code. So typically, what we can do is we can define, for every one of our pointers that we pass through, we can define an eigen map object that is going to give us, it's going to give us just an interface to accessing the data in that pointer. So what we can do is we can use different eigentypes for these different things. So the first thing that we're going to be using for this train input matrix is going to be an eigen matrix X D object, and that object is going to be just a thin wrapper around this train inputs pointer. So we're going to call it train inputs map, and the initializing the values we need to use in this constructor function here are the pointer where the data is stored and the dimensions. So that's going to be n observations by n features. And so let's just recompile that now just to see if that's actually the right syntax. Invalid conversion from const to double to okay, I see. So in fact, Eigen doesn't like this having it being a const double pointer. So there's two things we can do here. We can cast this to just a double pointer, I think, right, and that works just fine. Or we can get rid of the const on the double pointer argument here. I prefer to just leave the well, here it's giving us an error because this definition here is now not agreeing with our prototype that we've defined in the other file, the header file. But I think it would be better if we just use the cast here. So then we can still keep this information that the const here is indicating that it's the input to the function. Anyway, so going on, we can do this. We can do this for also the test input pointer. So we can use a VectorXd object. So the D here indicates it's a vector of doubles and a matrix of doubles. And so here I'm going to initialize an object called train input. Sorry, this is going to be test input vec, and this is going to be a casted double pointer test input pointer, and it's the size of this vector is n features. So so let's recompile that, make sure that's working fine. Works great. And so what these Eigen map things do is it's just saying that, okay, well, we already have a pointer with some data created. The eigenmap is not going to make any copy of that data. It's just going to give us an interface to access the elements of that data in a nice way. And so, so what we're going to do is we're going to write this for loop over all of the data points from I equals 1 to n observations. And what we're going to do is we're going to compute the distance between one of the rows of this matrix. So that's going to be train inputs mat dot row I, and so we have to take the transpose so we can get a column vector that is the same dimension as this row vector here, the test input vec. So this is going to give us a vector of differences, and we're going to compute the norm of that vector with this nice norm method that the Eigen library gives us. So this is computing one of the distances that we need to compute the nearest neighbors. This is the distance between the test point and row I, the observation I in the training data. And so to save that distance to, we need to save that distance to a vector. And so what we're going to do is we're going to create a new VectorXd object with n observations, and one for each. So that's going to be a distance. Sorry, let's call that dist vec. So that's a distance for every one of the observations between the observation and the test data. And because we didn't put this VectorXd inside of a map, right, it's just by itself here, that means we're actually going to be allocating a new dynamic, we're using dynamic memory allocation like new or delete or free and malloc to do to get a new vector of an observation. So this is actually using new memory. And the other thing that we're going to do is we're going to get a vector xi of, let's call this sorted index vec, also of n observations. And this is going to be a vector of integers, and because of this I at the end here. And so what we're going to do is we're going to first store these distances in this vector, and then we're going to sort these indices according to the corresponding distances in order to get to figure out which one of these observations are the nearest neighbors. So to do that, we can use dist vec I on the left side of this equality here. And here, what I'm also going to do is initialize this sorted index vec I. We're going to initialize every element to just the same index. So it's going to be just the indices from 0 to n observations minus 1. Let's rebuild, see what happens. It works fine. So now after we've computed these distances here, what we need to do is we need to sort these distances in increasing order. So we can use standard sort to do that. And so what we're going to do is we're going to sort these sorted index, well, they're not sorted yet, but we're going to sort this vector so that it is sorted after we're done. So the first argument to standard sort is pointer to the first element you want to sort. And so you get, so here this sorted index vec here, it's a vector xi object, which defines this dot data method, which actually gives you a pointer to the underlying data. And you have sorted index vec dot data plus sorted index vec dot size, and so that's going to be the pointer to the element just after what we want to sort. So this is the two items that we want to do. And so, I mean, if we just call sort like that, it's not really going to be doing with what we want, because right now it just has these integer index values, but we actually want to sort these indices according to the distances. So we actually have to give it a comparison function here. And so to define an inline comparison function, you use this kind of syntax where you start with these square brackets, then you use these parentheses. It's a function that takes two arguments, a left argument, a right argument, and it's going to return what we want to do is so each one of these guys is going to be one of the indices in this vector, right? So what we want to do is we want to select the corresponding distance out of distvec, and we want to return whether or not the left one is greater than the right one. So to do that, we would do distvec left less than distvec right. Right? So that should work. But so we're making a reference to this distvec thing, and it says distvec not captured. So this is kind of a new C++ feature. So to make, for this kind of inline comparison function to reference one of these objects in the scope here, what we have to do is we have to tell C++ inside of these square brackets that we're allowed to access that object. And to do that, we use this AND operator next to that variable name. And so recompiling like that. Lambda expressions only available with standard equals C++ 11 or a standard equals new plus 11. So that's a good point. So we have to actually turn on this this feature, and to do that, what we have to do is we have to go to the source folder, and we have to create a new file called let's see, it's going to be called Makevars. That's capital Makevars. And inside of that, we're going to have to tell it what version of C++ to use. And so we can figure out how to do that. Well, actually, what we can do is we can do help.start. And we can look at writing art extensions here. And then if we search for C++ 11, using C++ 11 code, well, what we need to do is we need to use cxx standard equals C++ 11 in our Makevars file. So let's do that. Let's try that now. Rebuilding works fine, because we told it now that we want to use the C++ 11 feature and so here that's what this compiler flag says that was just generated from what we did here. Okay, so going back here now, this is compiling just fine now, and what's happening is that we've computed the distances. And so what do we do now? We can now compute what are the nearest neighbors predictions. So in particular, I mean, what we can do is we can initialize a variable called total, which is a double precision number, and then we can write a for loop for int model I equals 0, model I less than max neighbors, model I plus plus. So what we're doing is we're going to compute the nearest neighbors, the k nearest neighbors models from one neighbor to max neighbors. And so we can define a variable int neighbors equals model I plus 1. And we can define it int row I equals, so this is going to be the row of the nearest neighbor, and that's going to be the index in this sorted index model I, right? So because now these, after we have called sort here, we know that the sorted index vec is going to have, well, the first element is going to be the index of the closest neighbor. The second index is the index of the second closest nearest neighbor, etc. Right? And so this is going to get the index of all the row number of the model ith nearest neighbor. And then what we can do is we can add to the total the train label pointer of this row I. Right? So this is the corresponding label of the model ith nearest neighbor. Right? And then what we have to do is we just have to save these test predictions here. Test predictions pointer. The model ith entry is going to be set to total over neighbors, right? That's going to be the nearest neighbors prediction. So let's rebuild. That compiles just fine. Let's rerun our .c code here on the R command line. And so indeed we see this is the these are the nearest neighbors prediction for this data set. But so actually, when going back to definitions here, sorry, our y here, it's indicating a multi-class number. And so what we've coded here is a nearest neighbors for just binary classification or regression. So this doesn't really make sense, actually. Sorry for choosing a bad example. But what we can do is we can say, okay, let's figure out, going back to our data set zip train 1. This is the first column of the entire training data set. So let's say which zip train 1 is in 0, 1. So this is going to give me indices of all the data points of which are 0 or 1. So, whoops. So for example, if we do zip train so let's see. Well, let's just look at a few of these. Head I01. So these are just indices, right? So how about we say train? Let's have the let's say x. So let's just use the first 5 elements of this thing as training data. So here, let's do that. So then our training data looks like, well, we have 3 1s and we have 2 zeros. So it actually does make sense now to use these data with our k-neighbors function that we've coded. And for our test x, let's look at, let's have it be the 14th item. So looking at looking at the, going back to our .c call here, we're going to be calling this, and we're going to get some prediction. So let's parse this a little bit. So if we add an argument here, so what I'm trying to do is to try to be able to access these predictions easier. And so yeah, so what we want to do is let's call this predictions. So if we give that a named argument in the .c call, we're going to get a named list. So result list .c. So then our result list predictions can be accessed like this. And so we can see that for k equals 1, k equals 2, and k equals 3 nearest neighbors, using this small data set, we're always predicting the 1 class for this test x point. And if we go back to our definition of test x, well, it was this 14th data point. And if we take a look at what the label actually was here, well, the label actually was 1, so actually the prediction is doing a pretty good job. Okay, so that's it for this tutorial, and hopefully you learned something about writing C++ code and using the Eigen template library to access data and compute distances. Thanks.